of an acute angle using a right triangle. Okay. This is, I mean, this is not calculus at all. Here's your right triangle. Here's your theta. And we'll just use the standard A, B, and C. The truth is that both angles in the right triangle are acute. So you could similarly do this for, like, let's say we wanted to call the other angle alpha. There's a tendency to use Greek letters in trigonometry. Explain how to determine the sine of an angle. So in words, the sine of theta is the ratio of the opposite side B and the hypotenuse C. Even though we're used to the sine of an angle producing a number, air quotes number, what it really is it's the ratio of two sides, specifically the opposite side and the hypotenuse.
Right.
And that's very important to explain. It's also a reason why sine, cosine, and tangent are unitless.
Right.
If you're 5 feet from the wall and it's a 12-foot wall, 13-foot ladder, these are in feet, but when you take the sine of theta, it's 12 feet over 13 feet. Then those cancel. So all right, I feel like that's
good.
Sufficient. I'm gonna. All right. List all the values of the sine function that you know. All right, and I'm gonna supplement this with the a picture of the unit circle and then provide the answers that they're looking for here. Let me do this. Okay, so here is your unit circle. Yay. Sine is the y values. Make this a little bigger. Sine is the y values. And the instructor's trying to be helpful here. They're saying, like, if you know that the sine of 0, for example, equals 0, the y value, they're saying, like, well, so does the sine of 2 pi. Okay, because it repeats. It's also the case, though, that it repeats over here. So let me kind of get through this list before I make any other statements here. So what they're looking for, let me try to explain it. They're trying to say the sine of 0 plus 2k pi equals 0, where k is an element of the integers. Have you seen notation like this before?
I have not.
Okay. So this 0 is this number we said here. 2k pi is 2 pi. That's the period. But because it repeats every 2 pi, it's really 2 pi, 4 pi, 6 pi, 8 pi, and so on. But it also goes the other direction. It's minus 2 pi, minus 4 pi, and so on. So what is represented here, and you're going to see this in all the numbers that we do, is that you have to supply this 2k pi in your answer.
Okay.
So I'll try and organize this better, but this is like your first true answer, this line right here.
Okay.
The next one that you're supposed to know is the sine of pi over 6, and that's 1/2. But it repeats every 2 pi. So your true answer is sine pi over 6 plus 2k pi, or 2 pi k if you prefer, equals 1/2, where k is an element of the integers. So this is like a double z. Z is the letter thing that's used to represent the integer set, which is a different course, but that is what's used. You've probably seen the real numbers written like that before.
Yeah.
It's the same thing. There's
Oh, okay.
one for rationals, irrationals, complex. And if you read a paper someday, you'll see symbols like that.
Okay.
Okay. So this is like the next line that you need to include. Okay. So we're just going to kind of skip that intermediate step. It's sine pi over 4 plus 2k pi is square root 2 over 2. You got to include this one. Then it's sine pi over 3 plus 2k pi equals square root 3 over 2, k element of z. And then we keep going, sine pi over 2 plus 2k pi equals 1. K is an element of z. All right, so now we've hit this 90-degree mark, and we got to keep going. So we actually need to go for each of these values here. So unfortunately, we are not even close to half done. We've got to do the others, but they're all of the same type. They're sine of the angle, whatever the angle you have, plus 2k pi equals whatever that number is on the unit circle.
Okay.
So you have to repeat it for each
Okay.
of these, and you have to choose the right, in this case, it's square root 3 over 2, then it's square root 2 over 2, then it's 1/2, and then you're back to 0.
Okay.
Would you like me to write all these out?
No, you're good.
Okay. Now there's one simplification you can make, which is you'll notice that both at 0, 0 and pi and 2 pi and 3 pi and 4 pi and 5 pi and 6 pi and forever, it's always 0 right there. So you could actually condense this first one to just k pi.
Okay.
If you want. And then you would not have to include that one there because it's already included.
Okay.
But it's a small, like, little thing. I don't know if instructor's looking for it.
All right.
Is that sufficient for
Yep.
question 2? Okay. Let's go see what question 3 has to offer. Sketch the graph. Okay. What I'm going to do is graph it in Desmos and get all the points that matter and snip that in.
All right.
So give me just a moment here to get that uploaded. We're going minus 2 pi, like that. And I'm going to grab all the important points that you will care about. You definitely want to include all of these in your picture. And there's not much more to say about that.
All right.
The explanation, if you need one,
I
is
don't
that
think, I don't think we need one
okay.
for that.
Okay.
First three aren't really explanation needed.
All right. All right, finally, we're up to some calculus. Find the Maclaurin series. Do not just copy. Boy. Your instructor is missing a very important thing here. It's the you probably have talked about in class that about the value that it's centered at. It's centered at x equals 0.
Right.
That's missing from here. So to do a Maclaurin series, you have to start, and I like to make a table. So f of x equals sine x, and then f of 0 equals sine 0, which is 0. Then you have to take a derivative. Here's sine is cosine x. F prime of 0 is cosine of 0, which is 1. F double prime of x equals minus sine x. Is that right? Yeah, it is. Sorry, I don't know why I'm losing my mind. F prime of 0. Are you still with me?
Yep.
Okay, sorry, I heard something like maybe you had exited the call. Sine of 0 is 0. f triple prime of x is minus cosine of 0. F triple prime of 0 is minus cosine of 0, which equals -1. And then the nice thing here is the fourth derivative, you switch from ticks to fours, is back to the original. Oops, that's supposed to be.
Right.
And the reason that matters is you don't have to redo all this. You know that the pattern is 0, 1, 0, -1, 0, 1, 0, because f4 of 0 is sine of 0, which is 0, and you see the repeats. So you definitely want to indicate that this repeats.
Uh-huh.
You've been doing some of this in class, hopefully.
Yes.
Okay. Okay, so there's a formula for Taylor series. It's f0 over 0 factorial x minus a. Actually, well, I'm putting stuff in. X minus 0 to the power of 0 plus f prime of 0, 1 factorial x minus 0 to the power of 1 plus f double prime of 0 over 2 factorial x minus 0 squared. And this goes on forever. And that's the general form of whatever it is. It's like Taylor series is, yeah, I don't know. Hopefully this is clear. Like, this is what it is. I
Yeah.
don't remember the formula, but so now how do we use it? And for this problem, well, you start plugging numbers in. Like, yours is 0 over 0 factorial x minus 0 to the 0 plus your next one is, what did I say? 1. What did it repeat? 0, 1. Yeah. 1 over 1 factorial x minus 0 to the 1 plus 0 over 2 factorial x minus 0 squared. Okay, plus -1 over 3 factorial x minus 0 cubed. That's as far as we got, right?
Okay.
So you see the pattern 0, 1, 0, -1. So we're kind of shortcutting this. The next one is going to be 0 over 4 factorial, and then it doesn't really matter, but I guess I'll write it out, 0 to the power 4 plus 1 over 5 factorial x minus 0 to the 5th plus 0 over 6 factorial x minus 0 to the 6th plus -1 over 7 factorial x minus 0 to the 7th. And what you should notice at some point, because you don't want to keep writing these because it gets really, really long. That goes to 0, that goes to 0, that goes to 0, and that goes to 0. Okay. And if it's not clear why, I can explain, but it's that 0 in the top left.
Well, I'm noticing a pattern of the odd numbers are
Exactly.
not going to 0.
So now we're gonna sort of, like, this goes on forever, but we're gonna kind of simplify here. We're gonna say, okay, well, it's really, and I actually prefer to write the factorial for a while. It's always x to the n, whatever
Right.
n is. So your first term is actually x to the 1 over 1 factorial plus, actually it's -1. I'll do it that way. Sorry, let me just get a little more room here. That's like, let me rewrite that. I don't like this is written. It's 1 x to the 1 over 1 factorial minus, and now we're grabbing this one up here, 1 x cubed over 3 factorial plus 1 x to the 5th over 5 factorial minus 1 x to the 7th over 7 factorial. What will the next one be? You see the pattern here. It goes positive, then it's negative, positive, then it's negative. So it should be plus 1 x to the 9th over 9 factorial.
All right.
Minus 1 x to the 11th over 11 factorial. And then this goes on forever.
Right.
Did your instructor graph the Taylor series of sine compared to sine?
I don't think so. Let me look. No, I don't, no, there's nothing here in my notes. So,
Okay, it's a really like amazing thing. You're like, oh my goodness, I didn't know that sine could be represented as a polynomial. It will blow your mind in the math sense. It will, because this is right here is how your calculator approximates sine.
uh,
It does not do whatever you thought it did before. It actually puts the number in here
right.
for that.
So that's the answer right there?
Yeah, there's also the way you write it with sigma now. So it's sigma n equals, I don't know. I'm gonna go
I have
one.
the equation is, sigma, n equals 0 to infinity. Yeah, right.
There's a lot of ways you can write that. You can start at 0 if you want.
Uh-huh.
It doesn't really matter. It's x to the 2n plus 1, I think, over 2n plus 1 factorial.
That's the Taylor series?
Oh, I'm sorry. And then there's a -1 here out in front to 2n plus 1.
I recognize that equation. I can't remember what it is though.
Oh, why am I struggling here? So when you put 0 in, you get 1, 2n plus 1. N plus 1, that'll do it. Okay. Yeah. There's a lot of ways to write it that are all equivalent. So what you're doing is you're trying to show how the exponents increase oddly. So that's the odd expansion 1, 3, 5, 7, 9, and so on. This is always either 2n minus 1 or 2n plus 1. The expansion of 0, 2, 4, 6, 8, so on, that's always 2n. And then the alternating part, the fact that it goes -1, 1, -1, 1 like that, it's either -1 to the n plus 1, or it's -1 to the n, depending on the order that you want. I may have got these reversed. Yeah, sorry, this one is right there. But if you want 1, -1, 1, -1, it's the second form. And these are shortcuts that help you on tests. You don't have to remember how to do it. But I don't know if your instructor is looking for this. Maybe they're looking for, I think this is fine, this line here, but they might want the sigma. And these are both equivalent, just one's indexed at 0 versus.
Okay.
Versus.
Ours is indexed at 0 in the
yeah.
in our notes.
You could be irritating and make it index at negative numbers and really like give it to the instructor, but
yeah.
All right. Okay.
I'm ready to move on, man.
Ready to move on? Okay.
Yep.
Answer the following questions in order to approximate the value of sine 0.8. Do you have enough information to use a right triangle to estimate sine 0.8? Sorry, I'm just reading it because I'm trying to look ahead here. Do you have enough information to use a right triangle to estimate sine of 0.8? So again, like I'll call this theta, and I'll call this, what did I say, A, B, and C.
Right.
So they're saying, well, sine of 0.8, well, we know it's B over C from our picture above, but what the instructor is trying to tell you that like sine of 0.8 is approximately sine of pi over 4, because pi over 4 is 0.785 and 0.785 is really close to 0.8.
Right.
And because you did part 2, you know that this is square root of 2 over 2. So the answer is yes. I don't know, like I think it's implied though, like actually to find it. Maybe that's part B. Oh, that is part B. So part B is
So
everything.
part
Like
A, would you just do what you did, or?
I would just say
Oh, okay.
yes.
Okay,
And then part B is down here.
but okay, okay,
It's like one leads to the next. Like,
right, yeah,
this is what she really wants, but maybe there's just a weird thing where. All right, so part C. I gotta grab a couple snips here. Estimate it using the graph. I'm gonna go back and grab the graph that we had from before. I'm gonna not get rid of all those. Go x equals 0.8. Let's go from -1 to. Oh no, I don't want to do that. So I'm just framing the picture a little more nicely to be able to. Okay. Here we go. So what I attempt to do here is this is 0.8 on the graph. This is x equals 0.8. And your instructor wants you to find that's x. They're saying do that. So they intersect right there. So if we go over to the graph, you can see I'm going up by 0.1s. So so sine of 0.8 is approximately 0.7.
uh-huh,
I think that's what they want you to say. But what you want to do is whatever you create for part. I'm gonna scroll back way back up here. Whatever you do here, you want to redraw the same thing for this part of the project.
okay. And just do the same thing you did.
Yes, like don't make the graphs because you're supposed to use that graph from part 3. Like
Oh, okay,
that's what I mean. Like don't draw a new one.
right,
Then it's like, oh, what's he doing here? He doesn't
right,
really understand. It's literally just where does it intersect the curve? It's just that point right there,
okay,
0.7. Nothing more to say there on that.
alrighty.
Estimate sine 0.8 using the 5th degree calculator. How many, just curious, like where are you at on Taylor series? Did you do one for like E?
Yeah, we did one for, here, let me look real quick. Yeah, we did one for like e to the -2x. I think we finished them. We're on polar coordinates now.
Oh, you're all done. Okay. All
Yeah,
right. Yeah, because the big reveal is that like there is no such thing as sine, cosine, tangent, E, ln. They're all Taylor series. They're all polynomials.
uh-huh,
All right. So this one, it says estimate sine 0.8 using the 5th degree Taylor polynomial. So this was what was missing in that part 2, maybe part 4, like they're supposed to give you the centering point. If they don't, you can't do it.
uh-huh.
At least I mean, unless, wait a second, maybe the instructor, okay, I mean, it slightly changed what we did here. Maybe the instructor meant, I'm looking back, like to just use a generic center of A. And if that's true, all of the zeros go to A's, except for the ones on the right here.
Uh-huh.
Well, no, that's not true either. Yeah, all these zeros go to A's. I guess if you have time, I guess you don't. I'd probably go with this, but it's very unclear. Because here it is clear. It's saying do it at a equals 0. That's your center. So that 5th degree polynomial we just found is x to the 1 over 1 factorial minus x cubed over 3 factorial plus x to the 5th over 5 factorial. That's your 5th degree down here. I know it's 5th because it's power of 5.
Mhm.
You have to be careful though. Sometimes exams will say 5 terms. and we don't have 5 terms. And it'll be sometimes
Right.
good instructions to say non-zero terms.
Mhm.
So if you get that on an exam, make sure you keep going here for that. Okay. Now, to find so what we're saying is sine of 0.8 is approximately equal to 0.8 divided by 1 factorial minus 0.8 cubed over 3 factorial plus 0.8 to the 5th 5 factorial. So you may use a calculator, but what the instructor means is this part on the right hand side is what goes in your calculator, not sine 0.8. So weird. All right. So we have x over 1 plus x minus x cubed over 6 plus x to the 5th over 120. You should definitely check this number, but I get 0.71740. Any questions about that? Comments?
Are you already done with that one?
Yeah, that's it.
Oh, okay.
Oh no, there's more. I'm sorry. Find the error bound from the alternating series using the next non-zero term. Okay, so the next non-zero term is the minus x to the 7th over 7 factorial.
Uh-huh.
So I believe you put 0.8 to the power of 7 into the 7 factorial, and your error is less than this right here. So your error is less than or equal to, they put absolute value because you could see here it's negative.
Right.
Now, I don't even know if the calculator will do this, but it probably will, but it's going to give us something factorial 7. So this is this number right here is 4.161 times 10 to the minus 5.
Okay.
So you grab that next term, and that's how you explain what it tells you about the actual value sine it. So it tells you, like, let me write, sorry, let me just get this framed better. So we think the answer is 0.71740. But if I write this one out, it's 0.123444161. It's saying like the answer is really this number you just found plus or minus this number.
Okay.
So it means because it like you're good up to the 1, 2, 3, 4th decimal place.
Mhm.
I don't know if you know about computer programming or care, but there's huge problems in programming because of like issues like this where you need more digits to store the actual number. And like you might not think that matters, but what if this is in something bigger than kilometers? 0.7174 kilometers, okay, but if your target is within a few meters, you need to have more accuracy than this, for centimeters. Even like it could matter. That's why this is important.
Right.
So one of the things in real life that you may find useful is like you sometimes want to give an answer, but then say, well, I only think it's good to this number, or I'm 95% sure that this is correct. You want to leave some room for, hey, there could be other things.
Right.
Which method do you prefer to use when estimating values of sine? I prefer to ask a friend. So it's usually better. I guess the choices here are right triangles, graphing the sine function, and then the Taylor series. And what I don't know is whether an option here is called the calculator.
Yeah. Right.
The best option is to use technology.
Right.
Because people build these things, they check them. We believe they're right.
Right.
If I didn't have a calculator, I would use a Taylor series.
Okay.
So it's kind of like, it's like in terms of accuracy, your accuracy improves as you go down this list.
Okay.
But in terms of effort, well, that's debatable. Like Taylor series are a lot of effort,
Right.
but the result is something that's pretty good, and you know your error. So I think like in terms of like what you probably should say this, because I
That's
think
the
that was
whole
that
thing.
was the whole point of this.
Yeah.
This is that. I mean, unless you got a compelling reason to upset your instructor.
Yeah.
Um,
Can
if
you
you
give
do,
like a little explanation as to why that's the
sure,
best?
let's do some typing here. Taylor series are computationally intensive because there are many terms, and oftentimes the calculation must be done with a calculator. Why did it lag right there? The benefit is that the error term is built into the calculation as the next non-zero term of the Taylor series. We could say that accuracy improves using the following approaches in this order. We say right triangle, graph, Taylor series, / comma calculator and calculator. Maybe that could be our first sentence here. And then we could say, the calculator is the easiest method. This is where you might want to throw in a link. And after some searching, many calculators, or we could say nearly all actually, use some variant of a Taylor series to estimate these values, which is true. But you should find a link or maybe quote your textbook.
Yeah.
I don't know, something. So let me make this a little bit bigger. Okay. And I think Taylor is capitalized. He was a real person, but he's dead now.
Poor guy.
A lot of old dead math and physics and
Yeah.
people.
Yeah. All right. Can we like go scroll back up and so I can see if like
Sure.
anything needs any more.
Where do you want to go?
Words next to it. Those don't really need it. I guess more the bottom ones. Keep going. Keep it going. No, that one's fine. That one's fine. I guess just like a couple words. It's like why you're doing each step, maybe.
Yeah, let me try that here. So you're writing the non-zero terms from above, from your formula from above. That's what you did here. This is the error term. It's the next non-zero term.
Okay.
And then we're evaluating at x equals 0.8. And we did use a calculator here. And then this is the next non-zero term, but we evaluate at x equals 0.8, the same value. It goes in both places. And that tells you, this is your estimate plus or minus your error term.
And that gives you what?
Well, it's like your answer could be this number plus or minus this error term. And it tells you that because you're not adding to the first 4 digits, your first 4 digits are solid. So in terms of kilometers, like, because let's just say this was answers in kilometers. I'm sorry. Kilometers. We know that that's 0.7174 kilometers for sure, which if we were translating it to meters is 717.4 meters. So let's say you want to launch a projectile, you're going to be within this place of meters. So the 100th place of a meter is like, I don't know, it's between you and maybe I don't know, as far as you can reach out your hand. It's not very far. It's pretty accurate.
Right.
Are you firing any weapons at the school you're at? Is that part of the training? I don't know. They're in some sort of, I thought you're in some sort of military school or.
No.
No, you're not doing anything like that. Okay.
No.
Yeah. All right. I was just thinking like, it's a pretty narrow target if you're firing something at.
Right. So. I think that's it, to be honest.
Great. Well, thank you again for scheduling. I'll send you the notes here right away so you have them. And let me know when I can help again.
All right. I'm gonna schedule probably tomorrow and then like Monday and Tuesday.
I don't have anything on the books tomorrow, so send me a text if you want me to put something up for tomorrow.
Final exam for calculus is on next Wednesday.
Okay. Sunday's also an option. I do Sunday, Monday, Tuesday, if that helps you.
Okay, cool.
You can take a look. All right. Thank you. See you next time.
All right. Thank you.